Okay. Let's get started with lecture 8. So the main focus of this lecture will be actually the Reed-Muller code and its properties that we have some sort of thing to complete. We need to recap the Elias-Bassalygo bound and prove the Johnson's radius. So we'll start off with that and then get into understanding the Reed-Muller code property. So we call it from the lecture. So, we've proved something called Elias-Bassalygo bound vector. So we redo the proof. And what was the bound said that for all delta in 0 half, if C is the n n delta n to code, then we have something very similar to the Hamming bound. The Hamming bound would have said R plus the binary entropy of what? Of delta by 2. So instead of delta by 2, we are going to replace this with Johnson radius. Is less than or equal to 1 plus this 2. Where what is the Johnson radius? Where J2 delta is half of 1 minus square root 1. Okay. So, and it's a sort of the proof of this was a generalization, it was a strengthening of the Hamming for the backing. What was the idea behind the Hamming bound? The Hamming bound said that if you had this of the ambient space, 0, 1 to the n, and these are your code words. If you drew balls of radius delta by 2 around each code word, then every word in this whole space participates in at most one code word. So we use this following, and why was that true? That was true because of the following idea. For all x, if you draw the ball around x with radius delta n by 2, and intersect it with the code, then the only element of then this was an at most a singleton. And why does this? So this is the property comes from the distance of the code, and because of this, if you drew balls of radius delta by 2, 1 second, I just clarify what a ball is. A ball is a ball of x comma set of all y in 0, 1 to the n, that the delta x comma y is less than 1. So I'm going to consider the open ball, not the closed ball. Well, so why is the back? Why does the Hamming bound follow from just this observation? Suppose we had this follows just from the distance of the code. Then I want to say that now if you draw balls of this radius around the code word, not around arbitrary points, around the code words, each point participates in at most one ball. Because if it had participated in more than 2 balls, then for that point, this will be violated. And anything Bassalygo bound just says what suppose we instead have the tau, suppose tau and L satisfy the following. That is for all x, we had balls. If you draw the ring around x and you look at tau n, this intersecting with the code, this is utmost of size n. Suppose you had this property instead. So in other words, if I draw these balls, it was possibly overlap. But sort of no point appears. What I want to say is, if this were true, then if you draw balls of radius gamma n around each of the code words, now let's ask how many times possibly a point appears. It's covered. I want to claim it's utmost L. Why? If it was more than L, then if you had drawn the ball around of radius tau n around that point, then there are more than L code words that well, you will see this. That's clear?
What breaks if this is more than N?
So what? So now I'm drawing the Hamming bond clear. Now I'm drawing balls of radius tau n around each code word. Now I want to ask. So there is overlap. There are points getting covered by multiple balls. Now I want to ask how many times. What's the overlap? What's the maximum overlap for any point? I want to say the maximum overlap for any point is utmost L. Say it's larger than L. Say there is a point which participates in say L plus 1 balls. Then take that point and go back to the statement. So that point, if you draw tau n radius, in other words, we just see.
Take one point and let's say it participates in more than L balls. No, that's not what we want to say.
No, this is the assumption. This is the assumption I'm giving you. So there are two things. This suppose tau and L satisfied the following. Now I do, this is given to us. Now I do the following experiment. Now I draw balls of radius tau n around every code word. That's that picture. That picture is not this. This picture is taken for every point. That picture is only for the code words. Now there's possibly overlap. A point possibly participates in multiple balls. I want to ask, what's the maximum number of balls the point can participate in? And I want to claim it's utmost L. Why is it utmost L? If it's more than L plus 1, if it's at least L plus 1, take that point and see more than L plus 1 and look at this assumption. For that point X, if you look at this, there are more than L plus 1 code words in the radius. So this will be violated if so if this condition were true, so I want to say star implies that if you draw then the balls of radius tau and around code words have a max overlap of L at any point. That's all I claim. So this will mean what the immediate response. What I'm saying is, the union of what I want to say is, if I take a ball C of tau n and sum this over all C in the code word. This quantity is at most L times the whole space because of what we have said. Because this union covers each point at most L times. Therefore, if we have this book. Now, just let's write the asymptotic version of this. It is just 2 power k into 2 power h2 tau n h2 tau and n is less than or equal to 2 power n plus log 2l, that is r plus h2 tau is less than or equal to 1 plus log 2l by n. So, as long as L is 2 power little o n, as long as that list size is 2 power little o n, then we more or less get the same. This factor does not matter at all. It hardly affects. Okay. So this sort of is stating that you're interested not just in the unique decoding regime. What is the unique decoding regime? Given a point and you're given a radius delta by 2, you want to find the code word if there one exists around that in that point. Now this is stating this is a slightly different problem. It says given a point, if you draw a radius tau around it, you give me all the L code word. This is the list decoding regime. And it sort of list decoding naturally makes its entry when you try to generalize the random number. And you want this, any this all the way up to size 2 power little o n is a meaningful result for this particular form. As long as you can come up with some tau and L pair for which the L is not exponential, slightly smaller than exponential, that's a tau and L pair which you can plug into this result and get this. So any tau that satisfies. So this is sort of list decoding. List decoding is the sort of the algorithmic question that is given an x and tau, find given x, tau is not given x, find all the code words in tau n. In general, this can be a, for example, if tau is very, very large, this can be this need not be an algorithmic question. The number of code words itself might be exponential. It states that because if tau is chosen such that happens, this will always be sub-exponential. You can expect. So in fact, most cases we see that L will not only be sub-exponential, it will actually be polynomial. So in which case you can actually show, then you can ask the algorithmic question. Now, given that the answer is polynomial, is there an algorithm that will find out all the code? That's the list decoding problem, the algorithmic list decoding problem. This is the algorithmic question. This will be just the combinatorial statement. And this the combinatorial statement, so that's the combinatorial statement corresponding to unique decoding. One over there, this is for list decoding. And similarly, later on in the course, we will ask both algorithmic unique decoding and algorithmic list decoding. Now, a question to ask is, so far it's fine. I said some tau and L, as long as the tau and L satisfies this property, we can prove such a bound. Now, what is the candidate tau that we can put here? That's my next question. Certainly, the one tau and L pair is delta by 2 and 1. That's what we got. Now the question is there a tau that I can put larger than delta by 2? And this is exactly what the Johnson radius term is. The Johnson radius is J2 delta. This is this magical number. We'll demystify it. We'll see the proof of this. We'll demystify the magic behind why this number appears. And what is the Johnson radius statement? It says, given any I've always delta in 0 to half, and C, which is the 01n code, 01n code. All I care is the distance of that code is delta. Then this property is satisfied. Then for tau be equal to J2 delta, we have that for all balls x, for all points x, all points x in 0, 1 to the n. The ball of x, tau n intersect 4 is at most of size n plus 1. That's sort of a common union. The Johnson radius is a number. It is, if you give me a code with distance delta, there is another number called the Johnson radius. And it's not hard to see that this number is always, we saw this last time, this number is always greater than delta. There's another number such that even if you go all the way up to that number, you will only see n plus 1 code, but you will not see more than n plus 1 code. Okay, that's the Johnson radius will repeatedly make its entry in this course. You see this number coming again. Today we will now prove this. We have all the tools to prove this. We have seen it. So is the statement clear? It's a number larger than delta by 2, a slightly larger radius. So that tells you that if you give me a code whose distance is delta, that means any two code words are at least delta apart. It says for this code, even if you go up to this larger radius, there will be no ball of this radius can have more than n code words, and more than n plus 1 code word that succeeds in. Now, of course, you could ask why is the Johnson radius this one? Can't we get a even larger radius? You can possibly improve the Elias-Bassalygo bound if you get even a larger radius. You can show, we will not do this in class. That is, you can show that there are codes with distance delta, so that if you go just above the Johnson radius, you see exponentially many code words. So as just a function of delta, if all that you know about the code was that it had distance delta, then this is the best you can say. That is, there are codes so that if you go just beyond the Johnson radius, you do see exponentially many code words.
This code somehow like natural or artificial there for
this one,
yeah, which
so the number will come out very naturally.
no, I know that there are codes which prove that you cannot improve this.
Yes. So those codes, yeah. So the way, of course, I will construct them, and construct them problems. I just construct a random code with certain properties to kill the Johnson radius. But this says this. But you can ask, of course, can you push? Okay, firstly, how large can J2 delta go? Firstly, it cannot go larger than delta. I want to claim, because if it goes larger than delta, Shannon enters the picture. You're saying you're going to make corruptions which are more than the distance of the code itself. And in that case, Shannon's actually, the proofs will say that you might have exponentially many code words. So J2, this tau can never be larger than delta. It can always be a number smaller than delta. Because if you make it that large, there will be points which will see exponentially many pairs around it. Now, so it has to be a number between delta by 2 and delta. So what's the number? Johnson's radius says that if you go up to that particular number, this number is called the Johnson radius. This is for the Boolean alphabet. There's a corresponding number for every query. This one. So the query, then if you go up to that radius, as long as the code has distance delta, you will not see more than n plus 1 code. Overlap. And the moment you go above it, there are codes for which suddenly the number of code words become exponential beyond the Johnson. But on the other hand, there are some very nice codes, so certain other codes which we'll see. Hopefully, we will see later on in the course that for which even if you go all the way to delta, don't hit delta, but go to delta minus epsilon, the list remains polynomial. There could be such codes, and in fact, we will show such codes later on in the code. Hopefully you will do this. But if you want a statement generically for every code, this is the best we can do. So to complete the proof of Elias-Bassalygo bound, what we need to do is show the Johnson radius. The Johnson radius has several proofs of it. What we will do, the proof which we will give will be inspired by geometric. In fact, it will very much be along the lines of Plotkin's bound. It will use the geometric lemma that we showed. That n+1 is basically going to come with the fact that we will show that we will come up with n vectors, all of what was the geometric lemma? If we had n vectors, all of whom were making obtuse angles with every pair, and the number of vectors is at most n+1, we will use exactly the same thing to conclude this. So given this setting, suppose this were false, we will come up with a setting for which this is right. But there are also, just like the Plotkin bound had a combinatorial proof, the Johnson radius also has a combinatorial proof. It's a nice proof. I'll see if I can push it in later. But Johnson radius is something we'll come to again and again. Probabilistic coding will be an essential part of our course in the latter half. We'll come back to Johnson radius. Possibly we'll do the combinatorial proof of Johnson radius later on in the course. That of Plotkin bound. So what's it again? We are going to have, so suppose we want to put a bound on this. So let's suppose there is some word in the space, and there are C1, C2, Cn, which are, so suppose there exists x 0, 1 to the n, and C1, C2, Cm belonging to the code such that Ci belongs to the ball. Delta Ci and x is less than tau for all. And we want to put a bound on m. We want to find the tau for which we can put a bound on. And the tau which will pop out automatically in the proof is the Johnson radius. Okay. We're going to do the same thing. We're going to do this Hamming distance to Euclidean distance trick that we did last time, that is in which a bit b is going to get converted to -1 to the power b. So we have this set x, C1, C2, Cn here. They map to x tilde, C1 tilde, m, Cm tilde. All of this are in ±1 of the power b. What do we have of this? What do we know? What do we know? The inner product of Ci tilde with Cj tilde is what?
Number of agreements minus
Number of agreements minus disagreements. So it's basically n minus 2d. So, and you know, so it's number of agreements, therefore, this is a number that is less than or equal to n into 1 minus 2 delta. Because this comes from the distance of the code. So these are all points which are close, which are PIC tildes are. They make a large obtuse angle with each other. But on the other hand, this is for all I not equal to j. And of course, we also have the fact that Ci tilde was equal to n. What about Pi tilde x tilde? So here it is greater than, because the number of agreements are far more than the number of disagreements. So here it's greater than n into 1 minus. Huh? X is an arbitrary point. So we assume that we want to prove this for every x. So suppose I give you an x and I have code words like this to satisfy the property. I want to find a tau for which I can put a bound on. So what is it? The proof will pop out, the tau will pop out in it. Okay. So if you look at it geometrically, what's happening in this proof? So you have this vector x tilde. And you're claiming that all the code words are sort of close, all the CIs are close to. The second one says, these are all, you can think of them all as unit vectors, or they're all of the same length, all the n plus 1 vectors will be like. This one, the last inequality says that they're all fairly close to x tilde because their dot product with x tilde is pretty large. So in other words, you have this sort of a picture over here. That is, you have one tilde sitting here, tilde sitting there. So they all sort of lie in this sort of a gap around x tilde. They can't go too far away from it. But amongst each other, they make a large this one. That is, if you take this one and this one, the dot product suddenly becomes large. So how from this you want to now appeal to the geometric lemma. So what would you sort of do? The point you want, I want to. So what we will do is we will just construct these new vectors vi, which is of the form ci tilde minus some alpha times x tilde. We'll choose a suitable alpha such that for all I not equal to j, vi vj is less than 0. So basically, I'm going to push ci minus alpha tilde is taking some vector of this type. And I'm saying if I can manage to do this, this will immediately tell me the number of the geometric. Now I can appeal to the geometric lemma and say the number of such vi's has to be almost n plus 1. This is what the question is, do we have? So let's look at this. So is the question, is there a suitable choice of alpha? So here is, can we find an alpha? The reals. Such that this happens, then can conclude m is less than or equal to n plus 1. That's exactly the geometric lemma we said last time. So what's this alpha? So let's go to it. What we want pi vj I not equal to j. This is exactly pi tilde minus alpha x tilde pj tilde minus alpha tilde. What do we have? This is pi. That's here. Let's write this on pi cj tilde minus alpha times x tilde pi tilde plus x tilde pj tilde plus alpha square x tilde. What's the bound that we can give on this? This is n into, I'm going to take out n completely out. This is going to be 1 minus 2 delta. At this point, it's actually less than or equal to because of. But then each of these are, it comes with a minus sign, therefore this is minus 2 alpha, 1 minus 2 tau. And now it's a less than sign, that's the less than sign, plus and alpha square. Fair enough? Let's rewrite this again. So this is n into alpha minus 1 minus 2 tau the whole square plus 1 minus 2 delta minus 1 minus 2 tau whole square. That's interesting written. That's but as long as this quantity over here is a negative quantity, we are done. The question is what alpha will I do? So you want to make it as negative as possible. So we'll choose, let's just choose alpha to be 1 minus 2 tau, this vanished out, and now just choose tau. So such that this quantity is. We our alpha have checked. So set alpha equals 1 minus 2 tau and tau such that 1 minus 2 delta is less than 1 minus 2 tau whole square. That is tau is less than half 1 minus 4. That's so if I accept if tau was this number, then I could have done. Okay, that's the end of it. And the exact same proof can be carried over for the two area. Have to be a little more careful, but you can do it. Questions on this? The Johnson radius is this magical number. It's well beyond delta by 2. It's a number that lies between delta by 2 and delta. So that even if you go up to that point, you will still not see, even if you make that many corruptions, you will not see more than n plus 1 code words. So in principle, it says, yeah, if you go beyond the delta by 2 regime, unique decoding fails because there might be 2 code words. But you can say, okay, unique decoding fails. You can ask the algorithm to return all the n plus 1 code words which go up to this point and say, you might use some other side information to find out what was your original message. It allows for even more corruption to happen in the, it allows even for, it says even under more noisy channels, I won't be able to uniquely recover the message, but I'll say the message is one of these n this ones, and then you can go and figure out using some other side information, which of these n pieces of information is actually the original message. And this one, so it sort of made its appearance in this proof of the Elias-Bassalygo one, the decoding notion. In fact, this decoding as a concept was introduced by Peter Elias, I think around the time he proved this. One, this was in around the 50s or so. But this decoding algorithmically happened only much later, only in the 90s. And we come to that proof. We'll show that actually the Reed-Solomon code, which we introduced 2 lectures ago, is not just uniquely decodable, it's also actually less decodable efficiently all the way up to the Johnson radius. Okay. Now we'll change gears. And move to the Reed-Muller. Notice we have seen several codes so far. We have seen the Hamming code, we have seen BCH code, we have seen Reed-Solomon code. We also seen some bounds, but none of these codes are actually good code. What is a good code? A good code is a code or a binary alphabet or a fixed alphabet, which has R to it's a family of codes, in which R and delta are both bounded away from 0. So you don't yet have such a code. All the code which you have seen, either R is 0 or delta is very close to half, one of these two things happen, or the Reed-Solomon code which had great, if you could get any R in delta, but the alphabet was very large. It was not a fixed alphabet. The alphabet was growing with one. We still don't have, we will not have at the end of this lecture. The Reed-Muller code will not be such a code. It will take us more work to actually come up with. So we've been drawing these curves and we are saying the Gilbert-Parshamo. The greedy code, of course, is there all the way on the Gilbert-Parshamo curve, and there are no curves to them. But we haven't yet come up with an explicit code anywhere in this thing. All the explicit codes are sitting on this, on the x-axis or the y-axis so far. They are very, very close here. There's nothing, there's no point. Forget about the curve. There is even a point like point not 1, point not 1. We yet don't have a code. We haven't yet come up with a code construction that's like this. And what we will do, the way we construct several other explicit codes which almost come to being good codes, but will have one bad property, either a large alphabet or the rate will be bad or the distance will be bad. And eventually, hopefully the next lecture on the next day, we'll show how to use these codes in combination with each other to finally get a good code. Okay, so now and we'll see yet another code, Reed-Muller code. So what was the Reed-Solomon code? Reed-Solomon code was, these are what are called polynomials. Reed-Solomon was a polynomial evaluation. So the message, you viewed it as the coefficients of a univariate polynomial. And the code word, the corresponding code word was the evaluation of this polynomial on some subset. This was the Reed-Solomon code. Now, what prevents us from just working with univariate? We can talk of multivariate things, talk of the same notion out here. That is, the message, you are working with multivariate polynomials. And the message you view it as coefficients of a multivariate polynomial. And that's how you view the message. And the code word is just the evaluation of this multivariate polynomial on all points in the space. There's nothing that this one, and Reed-Muller is basically exactly that. So the Reed-Muller, which was actually introduced before the Reed-Solomon code was introduced, is a generalization to multivariate polynomials. Okay, it's just going to be this. We will look at it in a little more detail in half an hour. So, in general, we will be working with M variate. M will be the number we're going to use for the number of variables. Therefore, there will be variables like x1, x2, and xn. The polynomials will have M in determinants. And we will be looking at polynomials. And in general, so we'll be looking at this. Is there now the corresponding ring of polynomials is this. The ring of polynomials. M variate, you're going to work with some field F being FQ. Q is some P bar R. Let me not call P bar R, let me call it P bar S. R is going to reserve it for something else. So the ring of polynomials with coefficients coming from the field. But as in the Reed-Solomon case, we will restrict the degree. We will not look at arbitrary polynomials, but polynomials of a particular degree. So I'm going to look at here, less than or equal to R, x1, x2, xn, which is the vector space of polynomials of M-variate polynomials of total degree at most R. What do I mean by this? Any polynomial here, P of x1 to x and looks like it looks like x1 to the power e1, x2 to the power e2, xm to the power em. It looks like sum and p e1, e2, em. Looks like that. But I want the total degree to be at most R. What do I mean by that? So I'm only going to look at vectors e1, e2, em, such that the summation of ei is less than or equal to R. But that's not the only condition I can be imposing. I should impose one more condition. Basically, notice that we are working in the field SQ. So x1 and x1 to the power q are the same. They are not going to be evaluated two different things. So then, if I allow E1 to have larger degree than Q or more, then two different polynomials will actually have the same evaluation. For example, x1 to the power Q and x1. They might be different as polynomials, but when I evaluate them on the field SQ, they agree everywhere. And because we are not looking at polynomials as polynomials themselves, we are looking at evaluations. These two polynomials will be the same polynomial. I don't want that to happen. So you want each of to prevent that from happening, we will set each of the EIs to be less than or equal to Q minus 1. So each EI is going to be a between 0 and Q minus 1. Okay. And now at least the two distinct polynomials will hopefully as evaluation vectors will not be the same. So this is going to be the fair enough. So this is what I could mean by M-variate polynomial of total degree R. Okay. And what's the code? The code is basically exactly how do I specify the code? We will view the message as giving out these coefficients. We'll view the message as these coefficients. Previously, in the Reed-Solomon code, the message was P0, P1, P2, all the way up to Pk minus 1, because K minus 1. Here we view the message as these coefficients. And then the code word will be just now, once you do the message, you have this polynomial, take the symbolic polynomial and evaluate it on certain set of points. That's going to be the code. In Reed-Solomon, we allowed an arbitrary set of points. In Reed-Muller, it is standard. Of course, here also you can allow arbitrary set of points. It is standard to actually evaluate it on the whole n-dimensional space. So the evaluation set will in almost all cases is just going to be a Q for the entire space. Most of it. Okay. There is a definition. So this code is what I'm going to call RM. Reed-Muller, Reed and Muller who discovered it independently. Q, which will tell you which field we are working with. M, which says the dimension of the ambient space, and R, which says what's the degree bound. Notice the degree bound here is less than or equal to. In Reed-Solomon, we made it less than K. And that was where, because that K exactly matched the rate. Here, anyhow, this number is not anything like the rate, so we're going to keep it. So, what is this? This is basically the evaluation vector of P of X, P of x1, x2, xn on the set FQ for M, where P is any point, the one in F less than or equal to R x1, x. So I've defined it very abstractly at this point. That is, go over all possible polynomials of this type and then take the evaluation vector of them. When you evaluate over the entire space of Q to the M, so that is going to be the Reed-Muller code. Yeah.
So can you use the R as follows that it will satisfy the equation R equals to M into Q minus.
What?
I can choose the R such that R equals to M into Q minus 1.
No, what's the equation there?
So I am saying that in the polynomial,
Yeah.
by the given constant, it might not contain the term only x to the power R. Right?
Yeah, R could be large, for example, okay, so there are two multiple cases. There is, if R were smaller than Q, then that it can contain. If R is larger than Q, it is not going to contain. Yeah.
So can you choose the R such that R equals to M into Q minus 1?
Is there something different happen or? Yeah.
Then it will contain the term x to the power xi to the power m, x to I to the power m, R equal in the polynomial set.
Then you get every polynomial.
Up to R.
Huh?
Every polynomial up to R, degree R, 12 degree R.
I still don't follow your.
No, I'm saying.
So suppose R is less than Q.
Then
Okay.
it will contain every polynomial.
No, it's not contained every polynomial. Suppose R is 5 and the Q is 10. Why will it contain every polynomial? It only contains things which are total degree 5. Yes.
And if R is bigger than Q,
Yeah.
then also.
So when will it? So as evaluation vectors, when will it contain all possible evaluations? So then you should remove the condition summation sigma ei is less than or equal to R and just let ei go for any number between 0 and Q minus 1. There are Q power n such, then the number of monomials will be exactly Q power n. And that's exactly the degrees of freedom you want. Every function is a function on, it has Q power n degrees of freedom. At every point you have a polynomial corresponding to that. So if you don't put a restriction on R, then if you just care about evaluation of polynomials, then it can go, the degree can go as large as Q minus 1 times n. So R will always be a number for us less than Q minus 1 times m. If R is greater than Q minus 1 times m, this is meaningless because it includes every function. And every function, that means if you are going to include every function, there will be two functions which are just have distance 1 from each other. We want code words to have distance. It will have every point in the every point will be a code word. So we don't want so if R will always be some number less than m times Q minus 1. Because if R is equal to m times Q minus 1, you are having every function as a potential code word, and then there won't be any distance. Okay. Notice I said things very abstractly. We will focus on various specific cases when R is less than Q, when Q is by Boolean. So to get our hands a bit dirty on what the Reed-Muller code is, we look at a few settings. But before that, I wanted to mention a couple of things before we enter into special cases. Let's first. So in all the cases, what I would like to understand is the dimension of the code. So this is the reason of the code. So notice what is the dimension of the code. Firstly, there are several things. It is an FQ linear code. That should be clear. Because you take two polynomials, you add them together, they are going to be this one. The next thing I want to say, what's the dimension of this code? That is the K. The dimension is a hard number. It's basically the number of monomials. That's the degrees of freedom you have. Of course, I'm assuming every two polynomials give distinct evaluations. Model, we haven't yet proved that, but once we have proven that, then the dimension is exactly the number of monomials. So it's basically, it's the size of the set. Size of the set we want to En belong to Z greater than or equal to 0 M, such that 0 less than or equal to Ei less than or equal to q minus 1 for all I, and summation ei is less than or equal to r. It's the size of that set. This is not necessarily a nice number. I don't have a closed form expression of it. It depends on what R and Q, because you're asking how many ways can I sum m quantities so that the sum is total R, but each quantity I can take it at most Q minus 1 times. It's not necessarily there's no clean closed form expression. So we'll see some special cases for this, for which there are clean closed form expressions. So let's look at
Get an upper bound with this ball, then you can get an upper bound.
So the question is, what is Q? These upper bounds, we need to have an understanding of what Q is. Q is, we don't even know what Q is. Q is also varying with M and R, so it's not an answer. Upper bound.
R plus Q minus
We'll see special set. Most of the upper bound we are talking about will happen for special settings, and we will see those upper bounds there. The two settings. What? For the binary case. So the two settings we will see are the following. One is the low degree setting, where R is less than Q. So basically R is less than Q, then it is only the last condition. The first condition can be dropped off. So it's easier to do it. That's one thing. The other that's one setting. The other setting is the binary setting. So binary setting. So here each EI is either 0 or 1. And then it's either 0 or 1, and then you have summation EI less than equal. So the binary setting in which Q equals. So one is the large field setting, and the other is the other extreme, go to the smallest possible field setting. All the intermediate settings are also interesting, but we will look at these two to just get a answer for this one. Because I also want to talk about the distance of the code. I haven't mentioned what the distance of the code is. Funnily enough, the distance of the code has a clean closed form expression for all Q, M, and R. And we will state that shortly. But first I will state it in these two cases, and then I will generalize it to state the distance for every Q, M, and R. So let's look at the low degree setting. R is less than Q. So the field size is large enough that it's larger than the degree that you're looking at. In this case, we can drop the constraints. Rather the summation EI less than or equal to R implies 0 less than or equal to EI less than or equal to 3 minus. So we can drop these constraints. We were interested in, but now the dimension should be easy. Now all you want are m numbers such that their sum is at most R. What's the number of ways of doing this? R plus Q. Why does Q enter the picture? So right now, it's actually exactly. In fact, I think isn't it exactly? So I want to say. So let's call this the dimension. I'm going to call it dimension, which is MQ. So let's call it KQMR. That number.
The last one is an equal to.
How many ways are doing this? I want to think this is just M plus R plus R.
Yeah.
Do you see that? This ball will basically you put M balls and R, either balls and bills, or you put it as M sticks and R stones. You arrange them on a line. How many ways of doing them? Basically, M plus R choose R, and then the first R things tell you what are you want to be in. The first R. You have R balls, everything before the R balls will tell you the size of the EX.
But take you mean the diagonal.
So,
but the quantity take you diagonal.
KQ, yeah. So this is what I mean. dimension of the code is 4. So in this case, the dimension of the code is nice. It's actually m plus r choose r. And we are yet to argue for the distance of the code. And this is the quadruple lemma. The quadruple lemma. Let P be f less than or equal to r, x1 to xn, r less than q, and P is a non-zero polynomial. I'm asking what's the probability that if I pick an A at random from Fq to the M, probability of EA is not equal to 0. That's the distance of the code. The weight of a non-zero code word is the distance of the code. So this is exactly, so what is there a lower bound that we can give for this? In the univariate case, what was the lower bound?
N minus or the
One minus.
1 minus 1 minus r by q. They can be at most r roots. Therefore, the number of times non-zero is q minus r by q, 1 minus r by q, and that continues to hold good actually. Notice you cannot afford to do better than that because a univariate polynomial is a special case of a multivariate polynomial. So the fraction of, so you could have a univariate polynomial which is just in one variable and two other variables. It's non-zero exactly 1 minus r over q fraction of the time. You can't improve this, and I want to claim actually you can exactly do this. I will not do this in class. I'll take three short lemmas. I'm not going to do it. You might have seen proof of short lemmas that have been good, or I'll refer you can see all the proofs are there. So the same thing is true even in the. So this is sort of a generalization of the degree mantra in the univariate case.
So for the special case, so
Yeah.
in this particular special case of the particular lemma and the evaluation case is just all of the field. That is directly followed from the degree bound because for any point x1 to xn,
Yeah.
that the univariate polynomial is lambda x1 to lambda xn. And this is a degree r polynomial in lambda. So this has at most r by q fraction of beta 0. So I need one dimensional.
Now, how do you know that when you what did you do?
So take any these different things.
Yeah.
You get a polynomial of lambda. F of lambda x1, lambda x2 to lambda x2.
Yeah. How do you know when you put this number, the polynomial doesn't become 0?
No, because at x1 to xn it is constant.
No. So if I give you the polynomial, which is actually x, so what's the polynomial you are looking at? You are looking at this. Which polynomial are you looking at?
From lambda x1, lambda x2 to lambda x2.
So you're making it univariate by doing this.
On this sub on and on for at least 1 minus r by q.
No. What is the polynomial of x1, x2, xn had been x1 minus x2? So you need to show on this substitution of lambda, the polynomial still remains non-zero. It could be that the polynomial becomes identically 0 on the substitution. If on substitution of this substitution, so you are moving from the multivariate case to the univariate case, and this substitution, if the polynomial continues to remain non-zero, you can now. I don't know how to a clever way to do this. The only way I know how to do this is use an inductive argument.
Generally going from multivariate to univariate while maintaining non-zeroness, that means there's no like simple. You can have said like exponential degree you can have for them.
So the only way I know how to do this proof, or there are multiple proofs I've seen of this in univariate case, is a case analysis. That is, either the substitution makes this identity 0 polynomial, you appeal to something. If it doesn't, it appeals to something, and you keep doing it. So the standard way of doing this is write p of x1 to xn as n-variate as a univariate polynomial in the last variable xm, the coefficients are coming from the previous variables. Now, either the choice of x1 to xm minus 1 makes the leading coefficient of this 0. In which case you can appeal to induction. This is a smaller thing. Or otherwise, it's non-zero, and now you have a univariate polynomial of degree r, and you can appeal to the usual degree method. So this is how I know how to do this proof. That's every proof I know is basically a case analysis of this. And basically it comes into this issue with, I do not know how to directly do in one step univariate. I don't know how to do a reduction because that after the reduction, I need the polynomial to be still non-zero. Okay, I will not do it. By the way, this proof, the proof which I just said, doesn't actually need. So this proof does not require the evaluation set to be SQ to the M. Any product set ES to the power M will suffice. And the corresponding bound will get equal 1 minus R times size of S. The proof statement. So sometimes people do study Reed-Muller codes even on product grids, not necessarily on SQL. Okay. So that's this one. Let's look at the other setting.
If I have a product statement just for each XI different XI.
You can do that. You can S1 to nowhere in the proof are you going to use this one. So actually, and they don't even have to be of the same sizes. You will put the sort of the minimum SI will be the size. You can take there's a version of it which even takes the size, all the sizes into account. Yeah. That is Q equals. So here, what is K2MR? K2MR is the number of E1, E2, EM in V greater than 0, so that each EI is either 0 or 1. And summation EI is less than or equal to 1.
Summation
M2. So this was just M2 up to R. Are you going from 0 to R? So this is M2 less than or equal. That's the dimension of the space in this setting. By the way, one thing which I did mention, this is right, you cannot improve it. I can come up with a polynomial that exactly agrees. In fact, univariate polynomial with this. Now I want a corresponding possible lemma over here. The same thing I have P belongs to this case F. That's the nature of the R and F to that to equal to F2 and E is not identical to 0. I'm asking what's the probability that EA is not equal to 0 when I pick A and a random point from this to 0. Okay, what's the smallest you can expect this to be?
Take a monomial, which is one.
If you what?
Take E to be a monomial of R variables.
Yeah.
then 1 by 2 power r.
1 by 2 power r. So certainly it cannot be smaller than, because let's take the monomial x1 to xr, the product of, that's the monomial. What fraction of the time it is? Is it non-zero? Only when x1 to xr are each 1, that's just 1 over 2 to the r fraction of the time. Therefore, you don't expect this to be smaller than this. This need not be just a monomial, it could be take any r independent affine forms and their product will give you the same thing. And this happens to be tight. You can show that these are that's the worst you can do. Every other thing will have larger than that. Okay, and the tight case for this is product of xi, I going from 1 to 1. Okay. So there are two different regimes of parameter. In one case, the large field, you have distance which is very close to 1. It's 1 minus r cube. That's like more like the Reed-Solomon setting. Whereas in small fields, the distance can be, you need to pick r to be small if you want the distance to be a well-behaved function. Otherwise, the distance is really bad for this. There are two different ones. There's actually a common generalization to both these. Common generalization. To be about two Schwarzschild lemmas. And once again, P is, so I'm not going to make any other thing, x1 to xn. P is not 0. And I'm interested in the probability that A is not equal to 0 when I pick a random point F2. Put a bound on this. The way I stated it would seem as if I sort of hooked up a sort of an interpolation between the two ends, and but it's actually a very natural system. So we will write R. So divide R by Q minus 1. So R can be written as Q minus 1 plus B, where 0 is less than or equal to B less than Q minus 1. You can do division, just the division, divide R by Q minus 1 to find out these numbers A and B. Notice in this case, B is R itself. B is equal to R and A is 0. In this setting, A is R and B is 0 in the binary setting. And what this happens to be is 1 by Q power A into 1 minus B by Q. Okay. Seems as if I just put this up, but I'll show you. Actually, I can show that this is tight. Why is this tight? So, just like we constructed the example of product xi, let's construct a polynomial which is going to be 0 most of the time. So, we want it to be 0 as much of the time. That was how we constructed that polynomial. So, let's try to construct a polynomial here. So one way to do this polynomial is, so I want to say it's going to be 0 for all choices of xi. I can't do that because then xi power q minus x. If I had to choose all choices of xi, I had to choose xi power q minus xi should be a factor of this. Not a factor, but the degree of this will at least be xi power q. And but I'm not allowing degree all the way up to q. I have to go 1. So let's make it such that
it's 0 for everything except the all zeros, the 0 point. When xi is anything other than 0, it's going to be 0. So what I want to say is, I'm going to construct this tight because of the following case, P of x1 to xn. For I going from 1 to a, I'm going to look at the polynomial, which is xi minus alpha, where alpha is not equal to 0. So for each of these xi's, I'm going to use alpha not equal. When xi is anything other than this, it is 0. If xi is anything other than 0, this polynomial vanishes. So I'm trying to make the polynomial 0 as much of the time, and then I choose one other guy, xi plus 1. Alpha j going from 1 to 2. So now I let xi plus 1 vanish 3 times. So now notice the total degree of this is exactly what is it? It is a times q minus 1 plus b. That's r. So it's a degree r polynomial. And when is it non-zero? Xi should be equal to 0. Xi between any number between xi between 1 and a should be 0. Because if it's not 0, it is 1. And xi plus 1 should be one of outside one of these events. So the probability for this particular polynomial, right, because of probability that this p a is not equal to 0 is exactly 1 by q power a into 1 minus b by q. See that? And so once you realize that this is the Schwarzschild lemma, the proof of this is not hard. The proof of this is almost identical to the same inductive proofs that we had for the other second. Invariably, I will not be using this. We will not be using this generalized thing. We will be using the GF2 setting or the low degree. Those will be the two. But there is a generalized thing for the, and there it matters. You have to do this. Divide r by q minus 1 and then have a new single.
So in the first part of the problem was alpha j.
So alpha j. So you think of FQ as alpha 1, alpha 2, all the way up to alpha 2. There are few elements.
And then the first one is alpha 1.
X I plus 1. So it's a polynomial only involving, sorry, it's xa plus 1. So if this, the first a variables are used here, and the a plus first variable is being used here. The a plus, you're trying to pack as to be 0 as much fraction of the time. So the first a variables, if the first a variables take any value other than 0, then the thing is going to be. So this, for example, this grid, this is going to be 0 everywhere except the 0 power a point. That's for the first a variable. Now for the other one, I would like to pack as much as possible, but the degree constraint does not let me. It only lets me go up to b, because I've already exhausted a into q minus 1 over here. So you put in b. Here you have taken q minus, you have taken alpha 1, you have taken q minus 1 guys over here. Here I'm taking just b guys, because that's how much the degree permits me to do. Okay. So this is a minimum weight code word for what the Schwarzschild lemma is stating is every code word has weight at least that, and because we have demonstrated this at this weight, this is the minimum weight code word for this in general rate R and Q and 1. Questions so far?
Okay, we talked about Reed-Muller codes and all of this. This is a linear code. Natural question is there a generator matrix or parity check matrix for this code? And generator matrix, I told you that the way I presented it is a generator matrix. What's the generator matrix for it? The evaluation is FQ to the M, and the columns are going to be basically the monomials. For every monomial, it's monomials versus this one. That's exactly the generator. That's the nicest generator matrix you can work for this. So all the Reed-Muller codes have this. The columns of the generator matrix are the evaluation points, in which case it's the CSS FQ to the power M, and the rows are indexed by the various monomials. This is a generator matrix. It's as nice as a generator matrix can get. What we want to now ask is the dual. I want the parity check matrix. For this, I need to understand the dual. And let's quickly see the solution. The Reed-Muller code has a nice property, like the Reed-Solomon code. So the dual of the Reed-Muller code is another Reed-Muller code. So its parity check matrix will also be similar such polynomial. So let's try to understand the dual of the Reed-Muller code. And we have already done all the necessary. Question?
I'm sorry, I just thought of it. Did we see the distance of the?
Yeah, those are exactly all these things. These are weight of the minimum weight code. These are the distances of the. So that's the distance.
Okay.
This is the distance of the Reed-Muller code. This is the distance in the GF2 setting, 1 over 2 to the R, and that's the distance in the. These are the distance. Yeah, because for linear code, it's sufficient to understand the minimum weight code words. That's the distance.
Yeah, okay. I mean, the code word evaluation method is telling us how many evaluations are you going to do.
Yeah. So notice we already observed this fact. Summation alpha power I. Alpha in SQ. As long as 0 is less than or equal to I, less than or equal smaller than Q minus 1. What was this quantity? This quantity was 0 if 0 is less than or equal to I less than Q minus 1, and it was minus 1 if I equals Q minus 1. This is something we saw.
Then alpha in FQ start.
Huh? No, I'm talking about FQ. This is what we do. What we will have to further do is we'll have to not just take. Here, this is just a univariate thing. We summed over all points. We will eventually have to take a monomial and sum it over all points there FQ to the M. So, right, this is what we know. We know this. So now let's ask the same question. So alpha 1 to the power E1, alpha 2 to the power E2, alpha m to the power En. I want to sum this over all choices of alpha 1 to alpha m in FQ step. Sorry, FQ. FQ per m. Notice that this just splits into a product. This is a sum of product, it just splits a product of sums. And if any one of them is, if any one of the EIs was less than Q minus 1, this turns out to be 0. So this is, by definition, is just product over I going from 1 to m, summation alpha I, e power I, alpha I in. And we can now just appeal to that and say that this quantity is 0 if E1, E2, En is not equal to Q minus 1, Q minus 1, Q minus 1. As long as it's not this monomial. But every other monomial, if I sum it up, this is going to be 0. Because there will always be one variable in which you don't hit the full degree, the Q minus 1 degree, and that variable will annihilate this, will ensure that this sum turns out to be 0.
So what does that mean? That means that suppose I take two monomials, x1 e1, xm em, and say x1 f1, xm fm. I take two monomials of this. Let's call this this a polynomial p. So let's call this a polynomial f, and this the polynomial g. F and G. And furthermore, I have that summation EI plus summation FI is strictly smaller than m times q minus 1. Then I claim if I take f of alpha bar, g of alpha bar, where alpha bar m, this should be because this is less than m to the q minus 1, there will be in the product there will be at least one variable in which doesn't achieve the full degree. So this in particular says, if what is the immediate corollary of this? Reed-Muller QMR, its dual certainly contains Reed-Muller Q m times q minus 1 minus r minus 1. The dual of this certainly contains this. Everything here is orthogonal to this. But let's actually, I want to say that the dimension of this guy and the dimension of this guy together sum to q power n. Why? I want to say the dimension of this object and the dimension of this object together sum to q power n.
So taking monomial for adding r.
Yeah.
X1 power u1, x1 power b.
Yeah.
So that the monomial x1 power p minus 1 minus q1, x2 power p minus 1 minus q2.
Yeah.
So that is a monomial for adding into.
Yeah. So the sum of these two are going to be always, so it's actually, so this is not actually a this one. What I want to claim is this is an equality. Matching dimensions. Matching dimension. You need to check this out, whatever theta are getting matching dimension. Actually get that the Reed-Muller dual is actually equal to
So just together they stand on space.
not to the together. So if you take all monomials of this guy and all monomials, or so take all monomials from this and all monomials, not these guys, but all the complementary monomials together, they will span the whole space. Hence, their dimensions together have to sum up to q power m, or at least q power m. You know that they cannot sum more than q power m because of this. That's the end of it. This is a nice fact to keep ahead. So the parity check matrix for the Reed-Muller code is also exactly these fq to the m on the columns, or rather fq to the m on the rows and monomials on the column, but monomials of this particular. If you're working in R, the monomials will go all the way up to this. So it's a very nice thing about the polynomial based code that they are their own duals. They are, since the duals, they are close. This family of Reed-Muller codes is closed on the duals. Okay. I'm going to take another 5 more minutes. I just want to give some specific examples of Reed-Muller code and then we'll wrap. I don't want to put Reed-Muller. Any questions so far?
If I interpret Reed-Muller code with the basic
So there will be a problem in the concept. It says actually the Reed-Muller code of where we'll do is actually a subcode of the BCH. So it's a smaller, the BCH code contains the Reed-Muller code. In fact, it's exactly a sub. So take the Reed-Solomon code over field f2 to the m, take R, and look at the corresponding BCH code. The Reed-Muller code will be a subcode of that
VCH code. It happens to be the case. I don't know if I'll put it in this problem set. This is the result of Pelican and Who. Pelican and Who. I will put it in either this problem set or the next problem set. This one. So the VCH. Now what I'm saying is the Reed-Muller code, I stated it wrong this way. Actually, Reed-Muller code is a subcode of the Reed-Solomon with a different field and a different. Okay. So, what we do next is some special cases of the Reed-Muller code. Yeah, so one special case, the first special case which we will see is say Q equals 2. I'm going to take the GF2 field, R being 1 and M argument. I'm looking at RM 2 M comma 1. What am I doing? I'm basically looking at the evaluation of all linear polynomials over the entire space, over the space 0, 1 to the power m. What do we know of this code? This is the block length is 2 power m. What is the dimension? It's m plus 1. It's all linear. So if m choose less than or equal to 1, that's m plus 1. And what's the distance of this code? Half. So it's 2 power n minus 1. That's a lower bound on the distance, but we actually showed that actually the distance is achieved. So this is actually 2 power n minus 1, 2 code. Yeah, so this special case is the reason I did this. This is what is called the Hadamard. So this is called the more popularly called the Hadamard code. And there's a reason, the reason it's called Hadamard code is the following, it's related to this concept. So now take these code words, these are 0, 1 code words. Take these code words, convert the 0, 1s to 1 minus 1 that we had done before, and let's put all the code. So notice that how many code words are there? There's one code word which is what?
Just linear polynomials.
These are just evaluation of linear polynomials. You take this matrix, you take this, so let's take a matrix in which the columns are all the code words. The columns are the code words. But I'm not going to put them in the 0, 1 world. I'm going to put them in the 1 minus 1 world. So what is this matrix? This matrix is actually a 2 power m plus 1 by 2 power m matrix. That's the number of code words in this one. This matrix okay. Let's do a special case of this in which so it's all linear function. So why does the word Hadamard code come? Hadamard code. So this is the evaluation of all linear functions, including linear functions which have constant term 1. That's why the m plus 1 comes. If you're asking purely linear functions, it's only m. Now let's look at the subcode which are just that pure. Let's look at this part of the thing which are just 2 power m, 2 power m minus 1. You can show that this also has distance half. Look at this code word. Now put this is a 2 power m by 2 power m matrix. If you look at it in the 1 minus 1 world, what's the dot product of any two columns? Any two distinct columns is 0 because of n minus 2d, that is, the distance is exactly half, therefore the distance. So H, this matrix, if I consider this matrix,
and I consider the matrix H2 power m, which is just all the column, all the code words stacked up. E2 power m code words stacked up. What do we get? That we get that H transpose is I. Not I, it's possibly m times I. It's 2 power m times the what? No, I'm writing it in 1 minus 1 word and then doing it. So I'm writing this, I'm putting P tilde over. Huh? Such matrices are called. So I want matrices which are just 1 minus 1s, which are orthogonal to themselves, are called Hadamard matrices. And one way to construct them is from these sort of codes. Okay. The Hadamard matrix. One more thing I want to say is that this is the Hadamard code. There's another code in which you can drop out the evaluation at the all zeros point. The drop evaluation at the all zeros point, 0 power m. So you will get this.
Minus one.
Huh? That's it, yeah. This is sometimes called the simplex code. I don't know why it's called simplex code. It's the simplex code. Let's take the dual of the Hadamard code, dual of this code. Let's take what the dual, what is the dual of RM2 and 1. We know this is actually RM2M. What is it?
U minus 1 minus R minus 1.
Yeah,
So M minus
M minus 2. M minus 2. So what is this code? This code is it's 2 power m, the block length. What is its dimension? It's m choose less than or equal to m minus 2.
M minus.
So it's 2 power m minus m minus 1. What's its distance? No, the distance is 1 by 2 power m minus 2. Therefore, the distance is actually 4. Okay. Yeah, so this is almost a Hamming code, except if you drop the evaluation in the origin. So drop the evaluation in the origin. So drop the evaluation at the origin. Origin, you're going to get a 2 power m minus 1, 2 power m minus 1. This dropping actually affects the distance. The distance drops by 3. In fact, this is one of the problems in the problem. If we drop all this from the distance might drop 3 code. And that is what we studied as the Hamming. Okay. So all of these Hamming codes, Hadamard codes are all instantiations of this Reed-Muller code, which itself is a special case of the Reed-Muller. So these are all, these algebraic codes come up with various. So I wanted to do a little more. I want to do some more examples, but that's fine. That's very well over time. We'll stop. Thank you.